Hello everyone, this is Dr. Giuliano. Welcome back. In this video we're going to be talking about ANOVA and variations of the ANOVA test. So first let's start off with our figure and let's find out where ANOVA is on the figure itself. ANOVA compares the means between three or more groups. So we'll start off with data type and we'll go to continuous. Then we'll see that there's going to be three or more groups, so greater than two groups, and we'll go down this line. And then there's different variations to the ANOVA itself. There can be paired versus unpaired test, and then there can also be one or two factors that are analyzed within an ANOVA. And we'll talk about what factors means later on in this video. So let's go to our first objective. Our first objective is to appraise if an ANOVA was appropriate for analyzing a specific endpoint within a journal article. So first let's define ANOVA and talk about what it's used for. And ANOVA is spelled out as the analysis of variance. And what it does, it compares the variance between groups within a study to the variance within a group within a study. And what this gets is the F statistic. Just like the t-test had a t-statistic, the f-test also has an f-statistic, and you will reject the null hypothesis if your f-statistic is sufficiently large enough. What an ANOVA does, it compares the means between three or more groups. So let's look at an example. Let's say, again, we're looking at weight loss with a new drug. And this time we need three groups. And we'll say we have 10 milligrams of the new drug, we have 20 milligrams, and then we have placebo. So I made a table to show what this looks like. We have 4 patients in each group, and the numbers in the columns there are the amount of kilograms of weight loss that these patients saw on the various treatments. Now, what we would do is we would run the ANOVA test, and if it is statistically significant, what this means is that there's a difference somewhere between one of these groups, but it doesn't necessarily tell you where. So if we have a p-value of less than 0.05 with our ANOVA test, this tells us that there may be a difference between the 20 milligram and placebo. There may be a difference between the 20 and 10 milligrams. There may be a difference between the placebo and 10 milligrams, but it doesn't tell you where the difference actually is. So if you get a statistically significant result with an ANOVA test, the next thing that you'd need to do is a post hoc test. So you only conduct this test if your p-value is significant or less than the alpha. Let's say we set our alpha at 0.05. If our p-value is less than 0.05, we'll have a statistically significant result, and then we can do the post hoc test. If they do a post hoc test with a non-statistically significant result, in the first place you should be very concerned and question the validity of the paper. 2 common post hoc tests. One is called the 2K post hoc test, and it's 2K HSD. HSD stands for honestly significant difference. And then we have the Sheffe post hoc test. Now, the Sheffe is more conservative, which means you'll be more likely to accept the null hypothesis. or you'll be more likely to show there is no difference between the groups. Now let's talk about some of the assumptions of the ANOVA test. Not surprisingly, our first assumption is that the dependent variable is continuous, which makes sense when we think back to our figure. We started with the continuous type of data. Our second is the sampling distribution of means in each group is normal. Remember, we're going to make sure that the standard deviation is not greater than the mean and that the sample size is greater than 30. Our third assumption is that the independent variables are mutually exclusive, which means they can only be in one of the groups. They can't be in both. The next is that the variance is similar between groups. Notice that these assumptions are very similar to the t-test. You can use the same rules for evaluating variance as you did with the t-test by looking for the ratio of variance between the groups. And then the last assumption is that the observations are independent. So let's work through an example problem. I will not be having you do the specific calculations for this test as they are a little bit more complicated than the t-test. However, I'll have you using an online calculator. So let's visit the previous example. Here's the table that I showed you before. What you can do next is calculate the mean and standard deviation. You'll need this for the online calculator. So I just quickly did this in Excel, so I'll grab that information. So our first step, as in previous videos, is to make sure no assumptions are violated. And let's scroll back up to our assumptions. The data is continuous as we're looking at kilograms of weight. The sampling distribution of the means in each group is normal. The standard deviation is much less than the mean. However, we don't have the sample of 30. We only have 4 in each group. So you would actually say it doesn't meet this assumption. However, we're going to pretend that it does. I just didn't want to use a huge data set because you guys are going to have to enter this into the calculator online. The independent variables are mutually exclusive. You can only be in one of the groups, and the variance is similar between the groups because the standard deviations are relatively close, and then the observations are independent. So we're going to pretend that we met all of our assumptions. We met most of them except for one. Remember, the next step is to state the null and alternative hypothesis. And in this case, it's the null is there is no difference in weight loss between the 3 groups. And the alternative hypothesis is there is a difference in weight loss between the 3 groups. Now remember, we don't know necessarily between which groups specifically the weight loss is occurring. We just know that somewhere there's a difference. Our next step is to state the alpha. Let's just state an alpha of 0.05. And our next step is to calculate degrees of freedom. So this is the point where we'll go to our online calculator. This is the same site that we used for the t-test. You want to go to this site and then click on ANOVA. That will take you to this page. I've already entered the data on this page, so you put in the number of subjects in each group, which we talked about was 4. We calculated the means and standard deviations for each group. now you can see the standard deviations aren't all that different from one another, and the means, it looks like there's a difference between some of these groups. So after we put this information in, we'll hit the calculate button. You get two types of degrees of freedom for ANOVAs. You get a between groups degrees of freedom and a within groups degrees of freedom. We'll use these two numbers to find our critical value for our F statistic, and then we get our calculated F statistic. So let's write these two down. So let's quickly find what our critical F value needs to be, and we'll go to a F table. This is our F table for an alpha of 0.05. The top row indicates the degrees of freedom between groups, and the column here shows the degrees of freedom within groups. So we had a 2 degree of freedom between and a 9 degrees of freedom within. This gives us our critical value of 4.256, which brings us to our fifth step, is find the critical value. And in this case, we said it was 4.256. The next step would be to calculate this test statistic. The online calculator already did that for us, and that value was 13.9 for the F statistic. And we know that 13.9 is greater than 4.256, so our results are going to be statistically significant. The calculations for doing the ANOVA and the variations of ANOVA get more complex, and it's something that I'm not going to expect you to do in this course. However, you should be able to repeat what I did in this video. This brings us to our second objective, and this is choose the correct variation of ANOVA based off numbers of factors analyzed if data is paired and if confounding is present. So first, let's talk about the numbers of factors analyzed. This is our example we were talking about. The only factor we're analyzing here is just the effect of the drug. However, we're evaluating the effect of the drug at different levels. So we see a 20 milligrams and a 10 milligrams, and then no drug. So those are 3 different levels. This is going to be a 1-factor test. So remember we talked about the levels, looking at 1 factor. Now we have another factor looking at weight loss, because perhaps we want to collect information on both and how both affect each other. And of course, exercise is an important part of weight loss. So we are now curious about both the drug's effect and then another factor looking at whether patients had a gym membership or not. So this is going to be referred to as a 2-factor, and you'll want to choose the appropriate test along with that. The way that this is stated within our figure is that this would be a 2-way ANOVA. Another variation of ANOVA is something called repeated measures. Repeated measures is going to be used for paired data, and we've talked about this previously. Let's say, for example, we have a patient that was given one treatment for a week, switched to another treatment in a following week, and then switched to the remaining treatment in the last week. Notice that the patient is the same in all of these groups. This is going to be an example of when you would use paired analysis, and the way that it's going to be expressed on our figure is called repeated measures. So up to this point, we've talked about our continuous types of statistical tests. we know that if we have two groups, we'll use a t-test, and if we have more than two groups, we'll use an ANOVA or some version of the ANOVA itself. We need to identify if the data is paired or unpaired and how many factors they're analyzing within the ANOVA itself. Our next set of videos will be going more into the non-continuous types of data or non-parametric data. And we'll be looking at both nominal test and ordinal or skewed continuous statistical test.